Dr. Anil Gupta is a professional engineer with more than 25 years of experience in the field of environment and natural resources in various capacities, including educator, consultant, technical advisor to the United Nations and in the government of Alberta. Dr. Gupta is currently working as Director of Environmental Modeling and Predictions with Alberta Environment and Protected Areas. Dr. Gupta is a recognized expert in the field of integrated numerical modeling, climate change, big data analysis systems, geographic information systems, and geospatial analyses. He has a distinguished record of contribution to scientific literature ranging from peer-reviewed publications to book chapters. Dr. Gupta is also an adjunct professor in the Department of Geomatics Engineering at the University of Calgary. He is actively involved in supervising PhD and MSc student research work, as well as principal investigator on various research projects. All right, thank you very much. If you want to get started, Dr. Gupta.
Thank you, Francine, for that very elegant introduction. So actually, like when someone says Dr. Gupta, it looked very strange to me because we use this title only when we talk to the academicians and other science experts. But feel free to just call me Anil or by my first name. So once again, good morning, and thank you very much for providing us this opportunity to present some of the work the department was doing since last almost like 4 or 5 years back. We started this work. So it is my privilege to present some of the work we are doing. And I also wanted to recognize some of my team members. They are on board. And actually, if you want to come, turn on your video and just say hi. Hyang, Hyang is a climate change expert actually, and he did most of this work actually. And I'm just basically presenting some of the work that has been done by my team members here. So Hyang is one of them. Thank you, Hyang. And Babak Farjad. Babak, you want to say hi?
Hi, everyone.
Thank you, Babak. And most of you probably know Tom Tang. So Tom Tang is a team lead, and Hyang and Babak, they work for Tom Tang, and actually, so we are part of one team here. And there are other team members are also there, which they are not present today here. I'm not sure, Francine, as I was talking to you, what is really expected, but I think what we're wanting to present here is some of the work that has been done by the department over 4 or 5 years, and this is all related to the climate change in Alberta, trying to understand how historically climate of Alberta has changed, how much change has happened in last, say, for example, 7 decades, about 70 years, and what we could expect in future. Okay, so the content of my presentation is and probably I need to skip many of these slides here, probably because I don't need to talk much about. Everyone is quite familiar and aware of some of these issues. And so why to study climate change? What are the needs? The framework we are using to study the climate change in our province, and then historical climate. So how Alberta's climate has changed in the last 7 decades. And here I will be focusing more on the Red Deer River watershed, and we don't have the analysis exactly for the Red Deer River watershed, but we have done the analysis at different scale, and one of the scale was land use framework region, and Red Deer River or Red Deer land use framework region is very identical to the Red Deer watershed, though there are some differences, but I think the Red Deer River LUF region analysis will mostly represent what might happen in the Red Deer River watershed as a whole. And some of we will be talking about the historical trends, what we have seen in our climate, in some climate variables. Then we will talk about the future climates. When we talk about the future climate, obviously everyone understands that they are global climate models. So what they are What are the challenges in applying those global climate models outputs, and then development of high resolution climate change data for Alberta, selection of representative climate change model projections, statistical downscaling, those kind of things we'll talk about. Then some of the trends in potential future climate of Alberta. Then I'm sure everyone might have heard about this global mean temperature, GMT. So the effect of GMT change in Alberta. So how Alberta, what will be the changes per degree GMT change globally, say for example. Then summary, some of the products, some of the next steps or what we are doing, mostly for the awareness. So why to study climate change? So what are the needs? So this is evidence-based. We have observing that there are changes in the hydroclimatic regime in Alberta. We have witnessing increases in the temperature, particularly during the winter time. Earlier snow melting and more frequent rain on snow-driven events and associated flooding, decrease in snow accumulation and summer flows, increased frequency and magnitude of extreme events like floods, forest fires, droughts. So these are all evidence-based. We are experiencing these at a greater magnitude and frequency. Then probably we are aware of that Paris Agreement that was 2015 Paris Agreement, where global efforts are there to limit the GMT or global mean temperature change to 1.5 degree. And then we know that the climate change science is evolving, is getting better and better. So we need to understand how vulnerable Alberta is to climate change. So that will include like understanding future trends and what that would mean to Albertans under different GMT changes. And finally, like evaluating the impact of climate change on water availability, water quality, terrestrial and aquatic systems in Alberta, so that we are able to develop proper mitigation and adaptation strategies. And this last piece, this is where the predictive modeling comes in picture. This yellow box here is basically recently, I'm sure many of you might have seen this national adaptation strategy that was released by the federal government, and they have provided a couple of examples like Hurricane Fiona in terms of evidence base, what is happening in terms of the extreme events. Hurricane Fiona, extreme heat waves and wildfire in British Columbia and Alberta, also drought and crop losses in prairies and catastrophic flooding in Ontario and Quebec, but also we know that that has happened in Alberta in 2013. So again, I have taken these two bullets from this national adaptation strategy that was released by the federal government. So what they are saying that the modeling from the Canadian Climate Institute estimate that Canada is expected to experience $25 billion in annual gross domestic product losses due to climate change in 2025, which is only 2 years apart. The huge losses are being estimated with respect to the GDP. And they are saying that without adaptation, the estimate rise to 78 billion and 101 billion annually by mid-century in a low and high greenhouse gas emission scenarios respectively. So climate change is going to cause a lot of losses in our country, and if we are not prepared ourselves for adaptation and mitigation. So our need started with the modeling. As I mentioned that my group does the predictive modeling, so we do the modeling. So our needs stem from the modeling perspective. So we know that when we develop the model, we have to hindcasting of the model. So we use the historical data to hindcast the model, and historical data, especially with respect to, say, for example, hydrological modeling, the climate forcing is one of the important data input. So we need to have a good grasp on historical climate data. And then to predict something in the future, obviously you need the future climate data. So we developed some kind of a framework to do some systematic work. So on the left-hand side, we all know that IPCC, they release the climate change projections. So they provide the future climate projections. And on right-hand side top, we have the instrumented records of climate. So we do the monitoring of our meteorology. So with respect to, say, for example, temperature, precipitation, humidity, solar radiation, all those things. So we have our historical instrumented record. So we use, so now, as you know that IPC, if you, like, there are hundreds of those global climate models are available, and they provide hundreds and thousands of those projections actually. So the first question is, like, what climate projections you wanting to use in your study, and what is the basis of selecting out of those hundreds of those climate projections which are available. So there is a need to do a selection of climate projections which are suitable or which are representative for your study area. So that is the one piece of work. So we do that selection of climate projections, and then using our observed historical data, we do the statistical downscaling and the bias correction to generate high resolution climate projections for the studied area. In this case, we have done for the whole province. And then all these data sets are now being used in predictive modeling. These data sets can be analyzed, and so we are planning to develop a web portal to provide access to all these data sets, some of these analyses, and some of the results of the predictive modeling in terms of the impact of climate change on water quantity, water quality, terrestrial and other systems. So this is our frameworks, and we are working within this framework. So let's start our discussion with the historical climate here. So obviously, as I said, that we need to have a good data set, good quality data set for our historical periods. And we know that our instrumented data sets are available at different stations. So there are different historical data sets are available, primarily the station-based data. Those station-based data, many of those institutions, they have taken those station-based data and they have produced the product called gridded data. So by interpolation, they have created the gridded data set. And there are some other data sets available called reanalysis, which are again kind of a modeled meteorology. So we developed some kind of a systematic framework to do some kind of a evaluation of all the available graded historical data sets for the North America. We developed a methodology called REFRES, Reference Reliability Evaluation System, and there's that methodology was published. And this methodology was based on, like, we have used different performance measures and also applied the multi-criteria decision-making method to rank different climate data sets using a technique called TOPSIS. And based on that methodology, we have developed a historical hybrid climate data set for the whole province for 3 climate variables: precipitation, minimum temperature, and the maximum temperature. These are the 3 climate variables frequently used in most of the hydrological models. So we have developed this historical hybrid climate data set for Alberta for last 70 years. So the period is from 1950 to 2019, and they are 10 kilometer by 10 kilometer grid. So every 10 kilometer by 10 kilometer grid in our province has a 70-year time series, daily time series. And the total number of grids in our province is about 9,365. But these data sets are right now available for our adjacent neighboring provinces or jurisdictions, because we know that we share our river basins with our neighbors. So this yellow highlighted area is the area for which we have this data set available right now. And then we have used these data sets to do some further analysis to understand how Alberta's climate has changed in last 7 decades. So historical trends in our climate. And obviously now, if you want to understand the trends and what has changed, obviously we need some kind of a climate indices. So we have applied altogether 43 different climate indices. 24 of those climate indices, they are temperature related. Out of 24, 12 are related with the daily maximum temperature. Another 12 set of 12 are related with daily minimum temperature. And this table basically shows or lists all those indices we are using. So some of these indices like TXX, this is the yearly maximum value of daily maximum temperature data. So this indices represent the extreme hottest or extreme or hottest temperature. And same thing, if you use the minimum data, then it will represent your extreme coldest. And then obviously we have annual mean maximum, annual mean minimum, and then seasonal values. So for example, in spring, summer, fall, winter. And all these indices are again recommended by IPCC. There is an expert team on climate change detection and indices called ETCCDI. So most of these indices are recommended by them, or they came up with these indices. And we have added some seasonal and some other indices to this list here. And these are 15 indices which we have used are precipitation related indices. So most importantly, most of the people they are interested in understanding annual total precipitation. And we are also using 4 multivariate indices that uses both temperature and precipitation. And we will be talking about this SPI, standardized precipitation and evapotranspiration index, also to understand the more like a water balance in the watershed. And just to inform you that in terms of how we detected this trend, so we have used a non-parametric approach, and we have applied the Mann-Kendall trend test, and the slope, that is the magnitude of change, has been calculated using Thielsen slope method. So in terms of the scale for our analysis, so our analysis started with the grid scale. So for each 10 kilometer by 10 kilometer grid within our province, we have analyzed, we have done this analysis, and then we are able to aggregate that analysis at a natural region scale. So as all of you know that probably we have about 6 natural regions. So we have the results for at a natural region scale. Then we also have completed this analysis for land use framework region and also for the provincial scale. So we are able to aggregate all our this analysis at a provincial scale. So for land use framework region, as everyone is aware about Red Deer River land use framework region. So this red geographic area is Red Deer LUF region. And this polygon here, the black polygon here, is the Red Deer River watershed. So the Red Deer River watershed is not entirely within the Red Deer LUF, but most part of the Red Deer River watershed is within the Red Deer LUF. So today I will be presenting the result of Red Deer land use framework region, which is the closest what we have right now for the Red Deer River watershed. But again, if required, we can reanalyze some of these data to produce very specific results only for the Red Deer River watershed if there is interest. Actually, feel free to ask any questions and feel free to interrupt anytime actually during my presentation. So some of the results with respect to the historical trend. So you will be seeing two different plots. One is specifically when we are aggregating the data for this Red Deer LUF region, and then we will be showing a provincial plot and with a map of Red Deer River watershed, so that you will be able to see like what is the spatial distribution of those changes. So for example, here, so this is the plot for annual mean minimum temperature. So if you aggregate all the grid cells within the Red Deer LUF and create one single time series, and then if you do the trend analysis as which might be a representative of Red Deer LUF region, the left plot shows the trend. So in annual mean minimum temperature, there's an increasing trend, and the slope of this line is about 0.28 degree centigrade, and this is the per decade. So over the 10 years, the change in annual mean minimum temperature is 0.28 degrees centigrade, and this is an upward or increasing trend. The middle plot, this shows the provincial, because we have done this analysis for the whole province. So this is the spatial distribution of the change for each 10 kilometer by 10 kilometer grid. So it is very hard to see that grid, but you are seeing that colors here. And there's a Red Deer River watershed. So, and then this is just the most right plot is just a zoomed one that shows the spatial distribution of the trend of this annual mean minimum temperature. So basically, wherever you are seeing the color and there's a scale in the middle plot, if you are seeing a color within the Red Deer River watershed, it means those pixels or the 10 kilometer by 10 kilometer grid is having a significant trend there, and the slope is here with this color here. So mostly if there's a red color, it means there's an increasing trend. The magnitude is you can see by the color, and if there's no color, if there's a white, it means there's no significant trend. It doesn't mean that there's no trend, but there's no significant trend. Still, there might be a trend increasing or decreasing, but the trend is not significant.
Hey, Anil.
Yeah.
A quick question here from Francine. Will these results be available to us in the future?
Yeah, sure. Okay. Yeah, you can share that.
It's kind of interesting to see that zoomed up version, relative to municipalities and that. Okay, thank you. Sorry.
Yeah. So, and as I mentioned, we have used 43 indices, so I will not go through all those 43 indices, but I will just show a couple of them, which we thought that people might be interested. So first one is the annual mean minimum temperature. The second one is annual mean maximum temperature. So again, there is an increasing trend. That the slope is 0.22 degrees centigrade per decade. And this right-hand side plot shows the spatial distribution. So we can see that in most of the area within the Red Deer River watershed, there's no significant increasing trend or decreasing trend. Only very small area, there is some kind of a significant increasing trend. Sorry. Okay. Yeah. So this table basically summarizes some other key results here. So I think you guys have seen this. I don't know if you guys are able to see my cursor here, the mouse. So I did presented these two plot here. Annual mean, that is the minimum, the slope was 0.28, maximum it was 0.22. This is per decade slope. So if you convert this per decade slope till now in last 70 years, so that means that annual mean minimum temperature has changed by 2 degrees centigrade in last 70 years. Annual mean maximum temperature has been has changed about 1.5 degree in last 70 years. There are some other indices, yearly maximum temperature, for example, this one. So in last 70 years, there was a change of 1 degree centigrade. But yearly minimum temperature, there was a change of 2.5 degrees centigrade. The biggest change that has happened is during the winter time period. So the minimum temperature or the mean minimum temperature during the winter time or during the winter season has gone up by 3.1 degrees centigrade in last 70 years. So winter has warmed up actually in last 70 years by about 3 degrees centigrade. So there's more changes that has happened during the winter time compared to the summer time. Oh, sorry, I should have this one here. Now, if you look at what has happened to the precipitation, so the annual precipitation, there was a declining trend, and the slope is 3.65 millimeter per decade. And again, right-hand side plot is same, shows the spatial distribution. So this is the annual, total annual. During the summertime, though there is a slight increasing trend, but this trend is not significant. During the winter time, there is a significant decreasing trend, what we have seen in last 70 years. And the magnitude is 4.87 millimeter. And I'm sorry to present these in 2 decimal with millimeters, but it just shows that, yeah, some of these like when you multiply by 7 decades, it becomes significant decrease in the precipitation. And we have, when you see the right-hand side plot, the spatial distribution, I think throughout the watershed, these precipitations during the winter time are declining. And here, this table basically summarizes the result. And if you use that slope and convert this in what might have happened in the last 70 years, so annual precipitation has gone down by about 25 millimeters. Summer precipitation, they have gone up by about 7 point something millimeter. Winter precipitations are down by 34 millimeters in last 70 years. And this table basically summarizes what we have seen so far and provide a little bit more information with respect to the seasonal distribution, winter, spring, summer, and fall. So the top value here is, say, for example, the warmest temperature, the hottest temperature, mean value is 32.6. They have gone up by only 1 degree centigrade. Coldest, they have gone up by 2.5 degree. Annual mean maximum by 1.5, minimum 2.0, annual precipitation down by 25 millimeter. But this here, if you see in the bottom, the winter, yeah, the 3.1 degree centigrade, so for example, minimum temperature. So the winter has warmed up basically compared to the changes that has happened during the other seasons, so especially during the summer. Now, talking about the future climate data. So I need to speed up here now. So global climate models, what are they? So probably probably everyone is aware of about these global climate models. They are the complex mathematical representation of global climate systems. They simulate the interaction between the atmosphere, land surface, ocean, and cryosphere, that is ice. And GCM depicts the climate using a 3-dimensional grid over the globe. So typically having a horizontal resolution of about 100 to 200 kilometers. And then there are vertical layers in the atmosphere and also actually in the ocean. So there are some challenges in directly applying the GCM output because there is a systematic bias in the outputs of the GCMs. The resolution is not good enough. They are very coarse. 100 to 250 kilometer resolution is not good for any watershed scale study. And again, there are too many GCM scenarios are available right now. They are combination of what they call shared socioeconomic pathway, SSP, and the representative consultation pathway, RCP. So there are so many different combinations are available and so many different projections are available. So not sure what to use and what not to use. So there is a need to select a subset of representative climate projections that capture the full range of future climate variability, because there is a lot of uncertainties. That's why all these projections are available. They are based on different scenarios. So it is hard to apply all these available climate projection in a particular study. So what we need to do, that we need to do a selection so that we are able to develop a subset. But also we need to make sure that our subset basically captures the full range of climate variability that might happen in future. And then the next challenge is we need, or the need is that we need to downscale these GCM outputs so that they are suitable for the local studies at the watershed or regional scale. This is just a cartoon kind of thing where we all know that with the coarser resolution, we have only couple data points in the watershed, and if we increase the resolution, we have enough data points for the watershed. So actually, we started with 41 climate projections, and again, when we started this work, the 41 climate projections were available, and so all this work is based on these 41 climate projections. Now there are more climate projections are available, so we might be able to repeat all this work. But yeah, as I said, the climate change science is evolving every day. More projections are being added. So in terms of selection of the climate projections, so we again developed a integrated geometric algorithm, and we have applied this high dimensional geometric algorithm for selecting the suitable or representative climate change projection for Alberta. And this work was also published. Yeah, there's a publication here. And then based on the application of this geometric algorithm, we, out of 41 climate projections, we were able to select 12 climate projections, which now we believe captures the full range of climate variabilities that exist in those 41 climate projections. So now instead of applying 41 climate projections, if we apply only 12 climate projections, we will be good to capture the full range of climate variability. And again, this is just shows the where those selected 12 climate projections they sit on this SSP RCP matrix. So I think looks like the algorithm has done a good job. They have selected all the extreme projections, from low carbon emission, low greenhouse gas emission, to the high greenhouse gas emission scenarios, and for sustainability SSP to fossil fuel based SSP. So after that, what we did the statistical downscaling, and again we have developed a in-house multivariate bias correction method. That method was applied to do the downscaling, and so all these 12 selected climate position has been downscaled for 3 climate variables, that is the precipitation, minimum temperature, and maximum temperature. And these downscaling was done for the period starting from 1950 to 2100. And again, there's a paper published on some of this work here. So all this work has been published. So again, results, same. I will be presenting the similar what I did for the historical one. So for Red Deer River, for Red Deer LUF, and then at the grid scale to see the spatial variability. So in terms of the temperature, so from 1950 to 2100. So this yellow part is basically kind of a past, and we are showing all, for the past we are showing our observed, that is our instrumented records. What it called historical is basically the historical data which are available in GCMs, and the projected is the future projection. So with respect to the annual coldest temperature, there will be an increasing trend. So this red envelope here, this envelope red or blue envelope, these are the envelope based on, as I mentioned, that we have used 12 different climate projections which we have selected. So this envelope is based on those 12 climate projections, and this solid line, either blue or red, is basically ensemble mean of those 12 projections. So that the ensemble mean, the changes based on the ensemble mean is about 1 degree centigrade or 0.95 degrees centigrade per decade going forward in the future. And this range is based on those 12 different climate positions we have used. So the range is right from 0.04. So some climate projections are showing that the change will only be about 0.04 degrees centigrade per decade. But some climate projections, they are showing that the changes might be as high as 2.04 degrees centigrade per decade. So there is a range, and this is the range what we are showing as an envelope. So this is the left plot. On the right plot, the same thing again. These are the spatial distribution, and again, the observed and the future. So observed is based on our instrumented record, and what we might have, what might be expect in the future is based on the selected climate projections. So the next one is annual mean minimum temperatures, similar pattern. Winter mean minimum temperatures, similar pattern. This is the summary here. So basically, if you, which one I want to pick here? So the last one, mean, like minimum temperature during the winter time. We are expecting that by 2100, based on the ensemble mean, the winter minimum temperature might go up by about 5 degrees centigrade. Our hottest temperature will go up by 4.3 degree. Coldest temperature will warm up by 8.5 degree. And there's an annual mean maximum 4.3, annual mean minimum 4.3. Precipitation. So in precipitation now we can see that it's almost like a flat curve here. Though there's an envelope there, but the solid line is not showing very significant. I'm not sure if it is a significant trend or not, but it still look very flat here. But it looks like the annual precipitation will have an increasing trend. So there we are expecting more precipitation annually. Though some climate positions are showing that precipitation will go down, some climate projections are showing that precipitation go up, but again, the ensemble mean of those 12 projections are showing that increasing trend. Spring precipitation, winter precipitation. Similar trends here. And this is the summary here. So I think the summer precipitation is expected to go down, but total annual and the spring and the winter precipitation are expected to go up in Red Deer LUF. What might happen in other LUF regions? So you guys might be interested what might be happening around our LUF, say for example. So, but the trends are consistent across the board. Then we'll talk about this SPEI. standardized precipitation evapotranspiration index, which is expected to go down. That means the things will become drier. So I will skip some of these plots here, but these are the plots for different LUF, for different indices, and there's a red deer also here. So talking to SPEI, so that determines the water surplus deficit, that kind of a water balance between precipitation and potential evapotranspiration. So these are for different LUF regions, and red deer is here, and we are clearly seeing that there's a declining trend there. Sorry, there's a declining trend there. So right now, on the middle plot, it shows based on the observed data, but decreasing SPI means dry condition in the future. So in future, the red deer LUF will become more dry. And so this one was SPI 12. So this is the water year. And we can also do this SPI for different time periods. So this next one on the left-hand side is for SPI 3 during the summertime, 3 months. So it's still the same result. During the summertime, we will see that there will be more dry condition. Right-hand side is the same plot you have seen before, SPI 12. And now what is the effect of changes in global mean temperature, GMT, in Alberta? So if global mean temperature changes to 1 degree centigrade, say for example, or 2 degree or 3 degree or 4 degree, how much it will affect? The effect in Alberta will not be the same. It might be a different effect in Alberta. So for example, for red deer LUF, with respect to hottest temperature, so 1 degree change of GMT will result in about 1.4 degree change in red deer LUF, so 40% more impact. Coldest temperature, 1 degree change in GMT globally will result about 2.2. So 2.2, more than twice the change we will see in red deer LUF. And again, some of these plots are basically showing comparison between historical and different GMT global mean temperature change, 1.5, 2 degree, 3 degree, 4 degree, 5 degree. So as GMT, for higher level of GMT, we are seeing that, yeah, the temperature will continue increasing. Winter temperature will also continue increasing. Some extreme events will happen. So for example, in terms of the precipitation, drought index, so SPI 3 and SPI 12. So more dry conditions are expected as GMT increases. So 1.5 compared to 5 degree, you see the difference. Same thing here, 1.5 to 5 degree for SPI 12. This is an interesting slide here. So written period of extreme drought occurrence in Alberta. So these are for, we have calculated for different SPI 3 and SPI 12, and for different GMT changes for different land use framework regions. Red deer is here. Right now for the baseline, the written period is about 15 years. So on an average, every 15 years, we might see there is an extreme drought in red deer LUF. But if GMT changes to 1.5, it will become 11 years. And if it changes to 5 degrees centigrade, it will become 4. So these occurrences will be more frequent droughts. Summary. So these couple slides and with respect to the summary, so I will skip them, but future climate trend, so prominent warming trend in temperature related climate indices and increasing trend in precipitation, but lots of uncertainties because all the climate projections, they are they are not agreeing with each other. There's a lot of uncertainties are there. But for the temperature, every climate position is indicating that, yeah, there will be increase. Frequent dry conditions are expected in future, large impacts on central and southern parts of Alberta in the province. Effect of global mean temperature, I think we talk about this. So these minimum temperatures, the coldest temperature will be about twofold for one-fold change in GMT during the winter time. Again, 1.5 degree. The frequent reoccurrence of the summer and annual extreme drought in future. The expected extreme drought return period is about 4 to 5 years under 5 degrees centigrade GMT change. Some of the products. So now we have the historical hybrid climate data set available for the province. We have the future climate change data set available for 12 climate projections that covers the entire province at 10 kilometer by 10 kilometer grid. We have applied the latest and the state-of-the-art technology to create these high-resolution climate data set for the province. We are in the process of completing 2 technical reports. So all these reports will be available once we are able to work with the communication and make them available in public domain. But there's a lot of papers has been published actually. So all of our work has been published and scientifically verified. Yeah, these are some publications. These are freely available. Some next step, we are working on making sure that these data analysis and knowledge, whatever we have created is available, is publicly available. We are also working on extending our historical and future climate data set to include additional climate variables like solar radiation, relative humidity, and all those things. Right now, we have only 3 climate variables. We are also working on understanding the impact of climate change. So translating the climate change data, what we have just created in terms of the knowledge. So what that would do to water resources in province, quantity, the quality, the terrestrial ecosystem, the aquatic ecosystem. So trying to understand the impact on these things. We also know that if climate is changing, so it's not only the supply that will change, but the demand will also change. So for example, agriculture demand will also change. And then the whole dynamics of supply and demand, I think we need to understand with respect to the climate change. Some work in progress. Yeah, we started working on extending our data sets. We started assessing the potential impact of climate change on hydrology. So we are focusing right now on to understand the water supply, the changes in the water supply. We are doing actually some modeling work in whole SSRB. We are working with Global Water Future. We are also working with private consulting companies like Equinity. We are working with academia also to develop different models for the whole South Saskatchewan River Basin. That includes RDRWA watershed as well. We are also just starting a project and trying to develop a forward-looking early predictive drought indices for drought forecasting in SSRB. Because most of the indices right now, they tell us there was a drought, but that doesn't help us. We need to know, we need to forecast these droughts in advance. Short-term, but preferably longer-term droughts. And we also started some work with Alberta Agriculture to understand the future crop demand under different climate change scenarios. That's all. Thank you for listening so patiently.
Wow, that was fantastic, and that was those were great slides for such a complex study. And yeah, I really appreciate that. We have time for a few questions. I'll just check the chat. If people want to raise their hand or